So our first speaker today is Zane Li from Indiana University Bloomington, and I will be the moderator for his talk. Zane's talk is titled Connections Between Decoupling and Efficient Congruencing. So Zane, when you're ready.
Okay. Yeah, thanks, Josh, for the introduction. Yes, okay. So let's first describe what Vinogrados mean value theorem is. So we're given two integers, s and k. S2s will be the number of variables that we have, and we consider k is the largest degree of the equation. We consider the following system, and we ask how many 2s tuples of integer solutions are there to this system right here, where the x1 and xi's and yi's lie between 1 and x. Okay, so you at least, there are some sort of trivial-ish lower bounds. If you let x1 be y1, x2 be y2, and all the way xs be ys, and have them range between 1 and x, there are at least x to the 2s many solutions. Okay. Second of all, there's sort of what I'm going to heuristically call the dimension counting argument, and you can make this rigorous. So if you sort of imagine the xi's and yi's to be random, then there are, maximum x to the 2s many 2s tuples. And the linear equation heuristically has a 1 in x chance of happening. The quadratic equation has a 1 in x chance, 1 in x squared chance in happening, and so on. And the kth degree equation has a 1 over x to the kth chance in happening. And so if you imagine that these are sort of independent events, then of these x to the 2s many tuples, you maybe should expect x over 2s times by the product of all these, which is just x to the half k times k plus 1. So then you can make this rigorous, and you show that this is also another lower bound right here. Okay, so these lower bounds were sort of very classical. And so the question is, what is the best upper bound? And the first upper bound was given by Vinogradov in 1935, who, if I remember correctly, just showed that the number of solutions is bounded by the lower bound times by x to the 1/2 in some regime between s and k. Afterwards, upper bounds on JSK were collectively known as Vinogradov's mean value theorem. So this was a term, I believe, that was coined by Hua in the 40s. So the main conjecture of Vinogradov's mean value theorem is that, which is now a theorem, is that this lower bound is essentially an upper bound. So in other words, that JSK is controlled by x to the epsilon times by the lower bound here. And if you notice that, so when s is equal, so when these two powers are equal, that occurs when s is half k times k plus 1. And so it suffices, that's the critical case. So it suffices to just prove that case. And the critical, yeah, so you once you prove that case, and then you interpolate, and then you get the whole estimate for all js and k. And so the quadratic k equals 2 cases classical, because if you go here, because it's just linear and quadratic, and the critical case just has 3 variables on both sides. So the quadratic k equals 2 cases classical, because you can just use the divisor bound. The critical k equals 3 case was proven using the method of efficient congruencing by Wooley in 2014. This is a very number theoretic argument, and the critical k bigger than or equal to 2 case was proved using L2 decoupling for the moment curve, which is quite harmonic analysis. And in 2017, Wooley used his efficient congruencing method to also give a proof of Vinogradov's mean value theorem for the critical k bigger than or equal to 2 case. So there are sort of 2 proofs, one using a lot of number theory, one using a lot of harmonic analysis. And so the overarching question I'm going to try to answer here is, how do they relate to each other? And in particular, sort of what can we learn from efficient congruencing in this decoupling language? And so to illustrate this idea, we're just going to concentrate on the quadratic case. Which corresponds, on one hand, the number theory side of things, I did say here that it's classical, but on the decoupling side of things, it would correspond to decoupling for the parabola, which is I wouldn't view that as quite classical. Okay, so let me define the number theory side. So the way that the talk is sort of going to be structured is that I first define the number theory side of things and go to the harmonic analysis side of things, and then hopefully we'll slowly maybe converge to something. J of x is the number of solutions to this system right here, where the xi's lie between 1 and x. Okay, so just to remind you how the heuristics work, how many solutions should I expect? The diagonal solutions give me x cubed. So I just let x1 be x4, x2 be x5, x3 be x6. And then the dimension counting argument gives me, so I have x to the 6 many possible 6 tuples. The linear equation has a 1 in x chance of happening, and the quadratic equation has a 1 in x squared chance of happening. So that also gives me x cubed. And in some sense, because these two powers are balanced, that's the critical case. And so E of z forever in this talk will be denoted as e to the 2 pi I z. And we would want to show that the number of solutions is controlled by x cubed. Okay, so both the efficient congruencing world and the decoupling world, to count number of solutions, we want to use some sort of Fourier analysis. And so the efficient congruencing world, they will write j of x as this mean value. So this is the mean value because it's the mean of this exponential sum over the square of the unit square. And so essentially this basically says that this exponential sum here exhibits square root cancellation.
Maybe this is a nice point to interject with a question. So someone has asked, does this relate to uniform random walk integrals?
I'm not sure what a uniform random walk integral is.
Maybe this is a good opportunity to have that person, Teodros, chime in with their question. If you could please unmute your mic.
Okay, thank you, Joshua. I think I can give you some information about it because it looks eerily similar to random walks.
Okay.
And there are actually, if it is really close to that, then, or the same, then there are, for certain dimensions, in your case, you're using dimension 2 here. Of course, you might add more. There are explicit formulas. So that means you can do better than estimate.
Right.
But I would like you to look at it later on.
Okay.
If it is related at all.
Okay. Okay. Yeah, I'll take a look at it. Yeah. Yeah.
Thank you.
Okay. Thanks for the question. Yeah. Okay. So so we can write the number of solutions to the system as this integral here. Basically, it just follows from just integral 0 to 1, e to the 2 pi ixn dx is just the indicator function of an integer being 0. In other words, basically what we want to do is we want to show that j of x over x cubed is bounded by x to the epsilon. And I'm gonna ignore these x to the epsilon powers and just use this notation to hide the epsilon powers of x or epsilon powers of whatever parameter I'm looking at and just write 1 here. So we want to show that j of x over x cubed is bounded by essentially 1. Okay. On the decoupling side of things, so we saw an exponential sum on the previous slide. Now, on the decoupling side of things, that should correspond to the extension operator. So we'll define that here. So j is an interval between 0 and 1, and the extension operator of j is defined by this integral right here. This is the extension operator for the parabola, because there's a c. This is right here. There's a c comma c squared. So you can write c comma c squared dot x. Okay. So notation. So we need to introduce the decoupling constant. So p of delta is the partition of 0, 1 into intervals of length delta. And d of delta will be the best constant that I can put into this inequality over here. So in other words, I'm just going to verbally describe what this inequality basically says and what d of delta measures. And it's just that, okay, so I have the interval 0, 1, and I have the parabola above 0, 1. And so I'm going to partition 0, 1 into intervals of size delta, so delta, 2 delta, 3 delta, and so on. And so then that lifts to pieces of the parabola that are these pieces. Okay, so d of delta measures how much does it cost to break up the extension operator of 0, 1. So how much does it cost to break up the extension operator over 0, 1 into these individual pieces of size delta? Okay, so d of delta measures how much does it cost to break up the extension operator 0, 1 into intervals of size delta in L2 measured in L6. The L6 here, so if you replace this L6 with L2, this would follow essentially from a disguised version of Plancherel, but we want to do better than that. L6 is also critical roughly for the same reason why the number theory case is also critical. So verbally, I'm just going to describe d of delta just measures how much does it cost to decouple 0, 1 into intervals of size delta, just to not say so many words, or say this in a sentence. So you want this estimate to be true for all functions g and for all squares of side length delta to the -2. And our goal will be to show that this decoupling constant is basically bounded by 1, okay, with this less than approximate. And Vinogradov, quadratic Vinogradov, would just follow by taking delta to be 1 over x and g to be the sum of direct deltas over here, because if you pick g to be the sum of direct deltas, then you would essentially, so E0, 1, g of this g here is just a exponential sum. So it should be I from 1 to x of E of I over x times x plus I squared over x squared times y. Okay, and then you want to measure that in L6, and then you do some appropriate changes of variables, and then you would get this estimate over here. Okay, so our goal is to say, how does the efficient congruencing proof of quadratic Vinogradov imply a proof of decoupling for the parabola? Okay, so both approaches, so decoupling for the parabola was, so for the paraboloid was first proved by Bourgain and Demeter in 2014. And both approaches, the efficient congruencing world and all the decoupling approaches for the paraboloid or the moment curve or for other surfaces, they all rely on some sort of multilinearization. The efficient congruencing world, it generally seems there's some sort of bilinearization, and on the other hand, in the decoupling world, there's some multilinearization, usually not bilinearization. But for the parabola, both the parabola decoupling proof of Bourgain-Demeter and the efficient congruencing proof of quadratic Vinogradov both rely on some bilinear object, and the proof I'm going to give here is somewhat different from both of them. Okay, so right here I wrote down the definition of d of delta just to remind you, because I'm about to define a bilinear decoupling constant. Remember, d of delta measures how much does it cost to decouple 0, 1 into intervals of size delta. And so we're going to bilinearize the problem as follows. So nu will be a parameter that's big compared to delta, but small compared to 1. So you should think that nu is of size delta to the epsilon. So MAB will be the best constant such that the following estimate is true. Okay, so let's verbally describe what this estimate says. So I have 0, 1, and I have the parabola, and I have two intervals, I and I prime. Okay, I is of length nu to the A, I prime is of length nu to the B, and A and B are positive integers, and I and I prime are at least nu separated. Okay, so these intervals are pretty far separated apart. They're like delta to the epsilon separated. Okay, and MAB measures how much does it cost to decouple I and I prime simultaneously into intervals of size delta. Okay, so I have two intervals. They're pretty big and they're pretty far separated apart. How much does it cost to decouple them simultaneously into intervals of size delta? Okay, so I know how much it costs to decouple one interval into intervals of size delta. So I can just apply that twice. But because I want these extension, see, the extension operator has like, an e to the 2 pi I in it. So you could imagine that if you put two of them together, especially two that are, the buzzword would be transverse, then they should exhibit much more cancellation than sort of applying the trivial bound. So the idea is that we want to put more cancellation together. So maybe there's much more cancellation in this MAB object than just this D of delta object. So, and I should point out this MAB object. So let's imagine that A and B are so large. So let's imagine A and B are so large that nu to the A and nu to the B are like of size big O of delta. So let's say, then what would MAB measure? So MAB would then measure in that case. So if nu to the A and nu to the B are so large that they're like 5 delta and 10 delta size intervals, then what I could do is I can just use the triangle inequality and show, and in that case, for those large MABs, MAB would be of size 1. So the game is to play, is to start from small a and b, which corresponds to large intervals, and I want to decouple them. And I want to move from small ab to large ab, which corresponds to small intervals. And so the whole game will be climb from small ab to large ab, and we're going to climb that like a ladder. Okay, so I defined a bilinear decoupling constant, and so I have to first show you how, and I told you that it might be useful. And I should also point out that if you illegally let I and I prime both be the interval 0, 1, which you can't by the conditions I've put down here. If you illegally let I and I prime be both 0, 1, then you would get this expression up here. So in some sense, this is a similar but bilinear-ish expression of d of delta. I need to first, the next thing I'm going to do is I'm going to show you that it suffices, the study of d of delta, which is our goal in studying, it suffices to just control MAB accurately. And so this is known as the bilinear reduction. And because it's a bilinear argument, all you need to do is Holder rather than what's known as the Bourgain-Demeter-Guth argument or the broad-narrow decomposition. In the bilinear argument case, you just need to use Holder. So we have the following application of Holder essentially. So basically says d of delta is controlled by 2 terms that are both advantageous. First, it's controlled by a term that is at a bigger scale. So this first term is larger scale. Okay, so we want to decouple. If this term was dominant, we went from delta to something bigger, and then we can just iterate this and move something bigger, 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 bigger until it's of size 1, and then we know how to decouple intervals of size 1. Okay, so that's one term. So it's a larger scale. That's beneficial. That's good. Or it's also bounded by a bilinear term, which has more cancellation, which is also advantageous. And so just to remind you what M11 means, M11 means that I have 2 intervals of size nu that are nu separated. So remember, nu is delta to the epsilon. So I have 2 intervals of size nu that are nu separated. How much does it cost to decouple them at the same time into intervals of size delta? Okay, and the proof is not so bad. So the idea is that you're just going to break up 0, 1 into so because it's a bilinearization, you're going to break up L6 into L6 over 2, which is L3, and then break up 0, 1 into intervals of size nu. And when I and I prime are close to each other, okay, you can think of the standard cases when I is I prime. Okay, then I can just apply trivial bounds, and sort of the buzzword is parabolic rescaling. In other words, I can just rescale the problem, and that gives me the decoupling problem at a different scale. So that's when the intervals are close to each other. And when they're far apart, well, that's how we've designed the definition of the bilinear constant, that then they're far apart, and their extension operators to jump ahead are transverse to each other. So we expect more cancellation. So that's the bilinear term. So this gives the large scale term, and this gives the bilinear term. Okay. So now basically and this is what I mean where we're going to start climbing the ladder. We start from small a and b, we want to climb up to large a and b. And the key is to climb up efficiently so that you don't lose anything. Okay, so what we've done essentially is reduce the study of d of delta to the study of a bilinear constant. Okay, so just to point out that, so this is inspired, so this is different from the Bourgain-Demeter proof. And this is a proof that's inspired from the efficient congruencing proof. So the particular exposition of efficient congruencing I'm following is Lillian Pierce's Bourbaki seminar notes, and she exposits in one section efficient congruencing and how it would work in the quadratic Vinogradov case. So there she uses an object which she defines as I of AB. And I of AB is this object over here. And so this is a kind of messy integral. So let me verbally describe you what this integral counts. So it says the following. So pick a residue class C mod P to the A. Pick another residue class eta mod P to the B. Pick them so that these are not congruent to each other mod P. Okay, and then this integral counts the number of solutions to this system over here, where C1, where X1 and X4 are congruent to C mod P to the A, and X2, 3, 5, and 6 are congruent to eta mod P to the B. Okay, so that's what this is what this integral counts, and then I aggregate all these counts with all the choices of residue classes C mod P to the A and eta mod P to the B, and I take the worst count. Okay, so that's what I of XAB measures. Okay, and in some sense, this is what inspired this choice of MAB over here. And just to illustrate that more clearly, so we had a residue class C mod P to the A. That's a residue class mod P to the A. Therefore, it's a p-adic interval of size P to the minus A. Therefore, over here we chose an interval of size nu to the A. Similarly, we have a p-adic interval of size P to the minus B. We chose an interval of size nu to the B. These residue classes are not congruent to each other mod P. So in other words, they're separated. That corresponds to that my real intervals are separated by nu distance. And of course, these exponential sums over here correspond to the extension operator over here. Okay, so earlier I mentioned how one should think of, so we would want, we should think that j of x over x cubed should be of size 1, and we should also think that d of delta, the decoupling constant, is of size 1. So morally, when we look at the efficient congruencing proof, we should think that j of x over x cubed should be thought of as d of delta. This is like some sort of commutative diagram of thoughts. Similarly, you can take this similar thought. So j of x, the fact that j of x is controlled by x cubed is a statement of square root cancellation. So you can think of roughly how big should I of AB be. So I of AB should roughly be, so this, if we pretend we have square root cancellation, this first exponential sum, the absolute value of this exponential sum should roughly be of size x over p to the a to the 1/2 times 2 because of the square. And the second term in the exponent, the second term over here should be of size x over p to the b to the 1/2 times 4. And so then we get that this is equal to x cubed over p to the a plus 2b. And so heuristically, at the end of the proof, we should expect that I of ab should be roughly of size x cubed over p to the a plus 2b with epsilon losses. Okay, so we normalize that because at the end of the proof, we expect MAB to also be of size 1 because it's controlled by the decoupling constant. And we also expect that this normalized I to also be of size 1. So when we look at the efficient congruencing world, we should think that j of x over x cubed should be d of delta, and we should think that this normalized I should be roughly of MAB, our bilinear constant. Okay, so this is an inspired choice, and you can ask, why did I choose 2 and 4 here? Okay, so 4 is not so important. 4 is just 6 minus 2. So if I wanted to prove, let's say L2, L5 decoupling for the parabola and not use interpolation with the critical estimate, I could just do 2 and 3. So 4 is important because it's 6 minus 2. 2 is important because I want to use Plancherel. And then another question you could ask is, what if I use 3 and 3? You can use 3 and 3. This is sort of very similar to what the Bourgain-Demeter proof of the paraboloid. You take their proof and restrict it to the parabola case. That's what that proof would roughly give. Their proof is slightly different because they use, well, you'll see. Well, I'll mention it in a bit. Okay, so I'm going to mention the key property of this, of the efficient congruencing step. And
maybe
what we're going to, sorry?
Just one more question. As you're explaining that numerology of the different ways to break up that L6 norm, there was a question about what about 1 and 5?
1 and 5. Yeah, so yeah, 1 and 5 doesn't, so 1 and 5 doesn't quite work, because see, roughly there are 4 steps of the, so it'll work in the key step involving I, but what will need to happen is that you'll need to interchange A and B, and in that case you will sort of want at least both exponent. You'll at least need this exponent over here to be at least bigger than or equal to 2. That's a kind of, yeah. What if you do 2, 2, 2? So that proof, yeah, so you could probably do that. That I haven't tried in particular, because I mean, you've had more multilinearization than you might need, so that might make things easier than, yeah, I haven't quite tried 2, 2, 2 before. Yeah. Okay, so the key step of the efficient congruencing world is, in the quadratic Vinogradov case, is to go from AB to 2BB. Remember, we start from, so the iteration is roughly as follows. So you go from 1, 1, and then we use this lemma and go up to 2, 1. And then there's that step where you interchange, and this is where it's convenient to do 2, 4, or 3, 3, or 2.5, 3.5. You want to interchange the 1 and 2. So this is just an application of a holder. Roughly it's just the integral of f squared g to the 4 is controlled by f4 g squared to the 1/2 times g6 to the 1/2. Yeah, so 1 plus 3. Yeah. So you go up to 1, 2, and then you apply this key step again, and you go up to 4, 2, and then you interchange and go up to 2, 4. You apply this key step again to go up to 8, 4, and then I think from here you've like slowly climbed up the ladder, and this is very efficient. And the reason why it's efficient, so you can ask why is this p to the 2b minus a? Why is this p to the 2b minus a sharp? And what you can do is you can normalize I on both sides so that they're of size 1, and you'll see that this p to the 2b minus a is indeed sharp. Okay, so I want to mention this proof and then mention how one could be able to one is able to translate this into decoupling. So I'll give 3 proofs of the, well, I'll sketch 2 proofs and give 1 proof of the translation. And mention which one I think is the right one. So let's remind ourselves what I of AB is. I of AB, remember, is this integral, this expression over here. So remember, so if I fix a congruence class C mod P to the A and eta mod P to the B, such that C is not congruent to eta mod P, the integral here counts the number of solutions to this system where x1 and x4 are congruent to C mod P to the A, and 2, 3, 5, and 6 are congruent to eta mod P to the B. And then I take the worst possible combinations of C and eta. In other words, this lemma basically says is that I want to control this count. I want to control this count over here by a count where 2 of them are congruent to something mod P to the 2B, because there's a 2B here, and the other 4 are congruent to something else mod P to the B. Okay, so that's how the number theory proof would proceed. And so because this system, so if A, B, C, D, E, F is a solution to the system over here, then it's pretty easy to see that 2A, 2B, 2C, 2D, 2E, 2F are also solutions to the system. And because I have the linear and quadratic equation, furthermore, 2A plus 10, 2B plus 10, all the way to 2F plus 10 is also a solution to the system. So this system is not only dilation invariant, it's also translation invariant. So using that property, it suffices to assume that eta is actually 0. So you just shift all, you want to count the number of solutions, the number of solutions isn't changed if you shift everything by eta. Okay, so this proof is quite number theoretic. I mean, it just uses mod. Essentially what we want to count is the number of solutions to this quadratic Vinogradov where the x1 and x4 are congruent to C mod P to the A, and the others are congruent to 0 mod P to the B. where C is not congruent to 0 mod P. So, x1 and x4 are congruent to C mod P to the A. So we're just going to write them as follows. And for 2, 3, 5, 6, they're congruent to 0 mod P to the B. So we're going to write them as such over here. Okay, so since they obey quadratic Vinogradov, the quadratic equation, this is the quadratic equation over here. If I just mod out by P to the 2B, so x2 squared, since x2 is 0 mod P to the B, x2 squared is 0 mod P to the 2B. So if I just take the second equation and mod out by P to the 2B, I get the following, okay? And then what I'm going to do is I'm just going to do difference of squares. So the difference is P to the A times y1 minus y4, and their sum is 2C plus P to the A times y1 plus y4. Okay, so here is where we're going to use that C is not congruent to 0 mod P. So since C is not divisible by P, then that means this whole expression here is not divisible by P. So therefore, all the powers of P fall onto this guy over here. And therefore, we've derived that y1 is congruent to y4 mod P to B minus A. So this is where roughly efficient congruencing gets its name, right? So a priori, I told you how many solutions are there with this property over here. And a priori, there's no obvious hidden conspiracy among the x1s and x4s. And then you insert it into the equation, and then there's this sort of, you know, hidden efficient congruence that allows us to efficiently count solutions to the system. And we can finish the lemma pretty immediately, because what we do is we choose y4 arbitrarily. So pick y4 to be any residue class mod P to the 2B minus A. So that gives me P to the 2B minus A choices. Okay, then that means y1 is fixed. So once y1 is fixed, once y1 and y4 are fixed mod P to the 2B minus A, then that means x1 and x4 are both congruent to something else mod P to the 2B. So you could write it out, but I won't. And then x2, 3, 5, 6 are still congruent to 0 mod P to the B. And then we just apply the definition of what I 2BB means, and therefore we're done. Okay, so you do this proof, and then you stare at it, and you try to think about what philosophically this means for decoupling. And so this is what I'll try to answer in the remainder of my talk. So let me remind you what the I object, this bilinear object that efficient congruencing uses, corresponds to this bilinear decoupling constant that I will use. So MAB, remember, is the best. So MAB, remember, is just that I have two intervals, I and I prime. I is an interval of length nu to the A. I prime is an interval of length nu to the B. They're nu separated. MAB measures how much does it cost to decouple them simultaneously into intervals of size delta. Okay, so that's how much that costs. Okay, so if we sort of believe, so the key lemma on the previous slide that I just mentioned to you, is there a simple argument if A equals B? Yes. Well, it should be, if A is B, then it should be the same argument, should certainly work. Yeah, the A equals B should be the first sort of hard-ish argument. Yeah. Okay, so if you take the key lemma on the previous slide and you just normalize everything so everything is of size 1, then you would basically want to prove that if A is less than or equal to B, you know that MAB is controlled by M2B, where I've hidden sort of delta to the minus epsilons and stuff in this less than approximate sign. Okay, so then the question you ask is that is this estimate actually true? And so if you unravel the definition of MAB, it suffices to show the following estimate here. So so let me mention how. So let's say I was able to prove this estimate over here. How would I finish? Well, what you would do is you would apply the definition of M2B here, and then things are normalized properly so that you will eventually see this right-hand side pop up. Okay, so it's enough to show that this estimate is true. It's enough to prove this estimate. So what does this estimate actually do? So this estimate says, I leave 4 variables alone. Okay, I want to basically find sort of diagonal behavior. I want to decouple I into intervals of size nu to the 2b in L2. Okay, and so in some sense, this is if you squint at the proof on the previous slide, this is essentially what happens, right? So I've left 4 of these variables alone, and I want to improve data about these 2 variables and this at a scale p to the mod p to the 2b, which is a p-adic interval of size p to the minus 2b, which corresponds to a real interval of size nu to the 2b. So in some sense, you squint at that proof and you're like, this is maybe the right estimate to prove. And so I'll sketch 2 proofs and give a third proof. So there are sort of 2 proof ideas that might jump out immediately. And the first proof idea is that basically you could go through the number theory proof that I presented and just replace all the p-adic norms with absolute values. So that will work. Getting it set up is slightly, I don't know, very slightly tedious. But once you see the key, the same numbers and the same scales show up. So you can replace the p-adic norms with absolute values. And so essentially is that you keep the 4 variables the same, and you want to break up I into intervals of size nu to the 2b. So let's just trivially expand everything as follows. And so if J1 and J2 over here are close, then I can just use Cauchy-Schwarz, and that gives me diagonal behavior. And the claim is that if these 2 intervals, if J1 and J2 are far apart, this integral here actually vanishes. And to see that, what you do is, okay, so assume that J1 and J2 are at least this far apart where C is chosen a sufficiently large absolute. So take C to be 1,000,000. That will work. So take C to be 1,000,000, and then you'll notice, and then you literally expand everything. So expand the definition of the extension operators and interchange the spatial integral with the frequency integral. And so then what happens is then if you observe carefully here, this is just the Fourier inverse of B evaluated at the linear C1 plus C2 all the way to minus C6, comma, the quadratic term. And so when I write sharp cutoffs, the indicator function of B, you should really think it's a Schwarz function adapted to B. So this is, so indicator function of B is roughly Fourier supported morally in a ball of radius delta squared centered at the origin. And so for this to be non-zero, you would basically need to require that this quadratic term is like less than, let's say, delta squared over 100. And similarly, this linear term is also less than delta squared over 100. And if J1 and J2 are sufficiently chosen large enough, then this inequality is violated. And you could write a proof that looks very similar to the number theory proof on the previous slide. Okay, so that's one idea. But you could imagine that, okay, that's nice, but this may not work so well with, let's say you replace 2 and 4 with 3 and 3. Okay, so there's another style proof, and then this is what I'll call the Bourgain-Demeter style proof, and it's a bit longer than what I just in this very small half slide that I described here. So one key estimate that the Bourgain-Demeter style proof will work for the paraboloid is that they will prove some sort of ball inflation lemma. The ball inflation lemma relies on some sort of key geometric fact, like some sort of multilinear Kakeya argument. The key geometric observation in our parabola case is just the following. So so let's say box, so I didn't write it here. So box is of size, is a nu to the minus 2b by nu to the minus 2b box. And T is a tube of size nu to the minus b by nu to the minus 2b. And T prime is another tube of the same dimension, such that the angle between them is at least nu. So for those that are familiar with the argument, basically that the extension operator is essentially constant on, various wave packets, and because my intervals are separated, that corresponds to the angle between these wave packets is at least nu. So cutting a long story short, the key geometric observation is this estimate over here, and it's just high school geometry. So the box is of size, it has area nu to the minus 4b. The intersection between the tubes has nu to the minus 2b divided by the angle between them. And the tube has, so this is nu to the minus 4b. The tube has nu to the minus 3b volume. And you square that because these have the same, these two have the same volume. And then we have a nu to the minus 1 here. And then if you compute it correctly, so on the right-hand side, on the left-hand side, I get nu to the 2b. So I get nu to the 2b over the angle. And on the right-hand side, I get nu to the 2b over nu inverse. And then the angle is at least nu, so therefore this is a correct estimate. And anyways, you can use this geometric observation to prove the ball inflation inequality and use that to prove this estimate as written over here. And so that would give a Bourgain-Demeter style proof. But I'm going to give a third proof that just relies on Plancherel. And we really actually use the 2 here, but not the 4, unlike in this proof 1. Okay, so to do that, and in some sense it already appeared in the Bourgain-Demeter style proof, is that I'm going to mention the uncertainty principle. So I've written the extension operator here. And so what does the uncertainty principle state? So if I is an interval size 1 over r, I'm going to draw a parabola. So I'm going to let I be this interval. Okay, I'm going to take the left end point, or take any point in this interval. I'm going to draw a normal vector. So that's the normal vector. And I'm going to draw an r by r squared rectangle pointing in that direction. Okay, so the uncertainty principle I'm going to use in this case is that for x and y in this rectangle, the absolute value of the extension operator of I is essentially constant on this rectangle. So pick any r by r squared rectangle pointing in the normal vector that you just drew over here. The extension operator of I is essentially constant on that rectangle, and it's a constant that depends on G, it's a constant that depends on I, it's a constant that depends on the rectangle, but the point is that it's a constant. So let's heuristically, let's maybe give a reasoning why maybe that this is a reasonable thing to suggest. So let's do the case when I is just the interval 0 to 1 over r. So when I write 1 over r, you should think that this is scale 1 over r, not truly 1 over r. So scale 1 over r. So I is interval size 1 over r, and so in that case, the normal vector is vertical. So so let's pick the vertical. Let's pick a vertical r by r squared rectangle, in particular this one. So why do we expect that this extension operator over here is essentially constant on this rectangle? Well, so we take our extension operator. We can write it. This is just using the definition. And okay, so C is of size 1 over r, x is of size r, so C times x is of size 1. So that means then e to the C times x doesn't oscillate so much. So let's just pretend it doesn't oscillate at all. So let's just cross it out. Okay. And similarly, C squared is of size 1 over r squared, y is of size r squared. So then C squared times y also doesn't oscillate so much, so we'll just pretend it doesn't oscillate at all and cross it out too. So we've canceled out we've just crossed out all the oscillation for convenience. And what happens is that we get this expression. And so this is a constant. It's a constant that depends, so it's a constant as you see, it doesn't depend on x and y. And it's a constant that depends on G, it's a constant that depends on my interval, it's a constant that depends on the rectangle that I was looking at. Okay, and so for other i's and for other spatial rectangles, you can just shift them to this case and you'll see. Okay, so using the uncertainty principle, I'm going to give a proof of this key lemma in that is the translation of the key lemma of the quadratic efficient congruencing case. Okay, and it just follows from Plancherel and the uncertainty principle. So this is the estimate we want to show. And so we have 2 intervals. I've already shifted one of them to the origin because remember, one of the first things we did in the number theory argument was pretend. So we had account solutions where 2 of them are congruent to C mod P to the A and the others are congruent to A to mod P to the B. Because the system is translation invariant, we could pretend eta is 0. So similarly, I can just pretend that one of the intervals is at the origin. Okay, so pictorially, we have one of our intervals here, and we have I as an interval here. So I is an interval of length nu to the A, and our intervals are at least nu separated. Okay, so and we want to prove this estimate. So this estimate says that we keep the 4 variables the same on both sides, and we want to decouple I into intervals of size nu to the 2b in L2. Okay, and remember this proof it does not use the 4 and only uses the 2. The 2 is the most important, 4 is just 6 minus 2. Okay, so we're just going to use the uncertainty principle. You can make this rigorous. So because we have an extension operator over an integral centered at the origin, or not at the origin, by the uncertainty principle, this extension operator is essentially constant on vertical nu to the minus b by nu to the minus 2b boxes. So in other words, to prove this estimate over here, what you can do is you take your big box B, okay, which is bigger than any spatial scale we'll ever consider in any argument. So what you do is you partition this big box B into intervals of size nu to the minus b by nu to the minus 2b. And then what you do is you prove the estimate on each such rectangle, and then you just sum up. You sum up because, you know, once you sum up in box, then you get this estimate over here. Okay, so without loss of generality, I'm just going to assume that this box is the nu to the minus b by nu to the minus 2b box is this rectangle over here. And so, yeah, okay, and then so all I did in this step over here is just all we did just here was rewrite what box is, okay, and then it suffices to just say that so this is the x direction, this is the y direction. We're just gonna in fact just prove we're gonna fix x, and then just prove this estimate in y. And then what we can do is we can just integrate over this, integrate in x, and thus we get this guy. So we just integrate over 0 nu to the minus b. Okay, where now I is an interval of size nu to the minus a, far away from the origin. Okay, and so now we have to actually prove something. All we've done is actually just rewrite and reduce and stuff like that. Okay, so let's prove this, and I claim this follows from Plancherel. So the extension operator over I, by definition, is just this guy here. And now x is fixed. X is fixed. So this is just some function that depends on x. And so what I'm going to do is I'm going to apply a change of variables, just eta is c squared. You can do it. I'm not going to do it. And so what happens is then you get a Fourier. You see a Fourier transform pop up, right? This is some Fourier inverse of some function. You can just write it out. And this is a Fourier inverse. There's an L2. Plancherel is now our key tool should be Plancherel. Okay, so let's mention that. So we're gonna partition. So this interval, so this interval here is what happens when I gets attacked by this change of variables. I'm gonna partition it slightly weirdly, but it's only because I want to undo the change of variables later. So I take this interval, and I partition it into intervals of this size. Okay. So it's d plus nu to the 2b squared and to d plus 2 nu to the 2b squared and so on. And if you compute these intervals are basically all of size, so d you should think of as nu. They're all of size d times nu to the 2b with smaller. So they're roughly of size nu to the 2b, but like slightly fattened by like a, you know, bounded constant, big O of nu. Okay, so we have, this is our expression over here. We rewrote it using the Fourier inverse. And the next thing we're going to do is we're just going to take this indicator function and put it inside the integral as such. And remember, when I write a sharp cutoff, you think of it as a Schwartz function. And then I'm going to apply Plancherel. Okay, Plancherel. Okay, so morally, this function is supported in a neighborhood, in a nu to the 2b neighborhood centered at the origin. So as j varies in this set here, okay, they're gonna basically they're only gonna have bounded overlap of size 1 over d, so 1 over nu. So so what you do is you just expand everything. It's a square, so you expand everything, and then because they have bounded overlap, you can just move the absolute values inside the sum, and therefore you get this guy, and then you undo all the Plancherel. You apply another instance of Plancherel, and you undo the change of variables, and then you get the right hand side, and that's the desired inequality you can do. So I'm a bit out of time, so for the moment curve case, you do something slightly more complicated, but that's for, I guess, another talk. Yeah. Okay.